Hello everyone and welcome to the 8th lecture in MEC 3430, Automotive Engineering Fundamentals. In this lecture we're going to look at suspension systems. So last class we looked at electric and hybrid drivetrains, looked at purely electric vehicles, hybrid electric, and then also looked at fuel cell vehicles, which is really just a subset of electric vehicles. So we're going to continue on for the rest of this course with our discussion of the mechanical components of the vehicles. We're going to look at suspension basics, wheel alignment, and then typical suspension systems along with their pros and cons. So suspension basics. So a suspension system is designed to serve several functions. We want to absorb small and large road impacts, protecting vehicle occupants from shock. We want to keep the vehicle on an even keel. In other words, the actual cabin, we want to keep it the angle to the horizontal as close to zero as possible, i.e. so it's not tilting all over the place over rough and uneven terrain, or when cornering. Ideally, when cornering, we wouldn't have the vehicle tilt at all relative to the horizontal. We want to ensure wheels follow road to provide maximum traction as there are those bumps and unevenness in the road. Ideally, we want all wheels to remain in contact with the surface for maximum traction. And we want to reduce the stress on the other vehicle components. We don't want the suspension to shake everything else or every other component in the vehicle and could lead to cyclic stress failures. So suspension must be able to withstand static and dynamic vertical loading of the vehicle. Dynamics have to be absorbed. Twisting due to forward acceleration and deceleration torque has to be able to withstand that. Has to be able to withstand thrust force due to forward acceleration and deceleration. Must be able to withstand any side thrust from lateral acceleration, side winds, etc. Now it's important to mention, just like the internal combustion engine section of this course, I'm only going to give an introduction to suspension basics. Everyone in the automotive engineering option will be taking dynamics this semester because of how this course has been moved around because of COVID-19. You'll be taking vehicle dynamics, and that's where you'll do a much deeper dive into suspension and actually the tools required to design a suspension system and looking at the forces and kinematics of suspension systems. So this is just going to be a brief overview of typical automotive suspension systems. Okay, what are some suspension terms? We have sprung mass. So the mass of the vehicle is supported by the suspension. We have the unsprung mass. That's the mass of the vehicle components not supported by the suspension. Wheels, tires, brakes, etc. Jounce or bump. This is the upward vertical motion of a vehicle. And rebound, the return of the vehicle to its resting position after a jounce or a bump. So if we look at our suspension system in terms of a simple mass spring damper system, we'll have our vehicle mass, which is our sprung mass. We'll have springs, which are connected to our unsprung mass and also to the ground through our tires. And we also have dampers. So we have our springs and we have our dampers to dampen the motion. The tire itself also act as another layer of suspension because the tires themselves will have some amount of spring and some amount of damping. So really the suspension system, the tires are part of it. But in general, we don't include the anything to do with the brakes or anything like that in the sprung mass because that's not actually supported by the main suspension system. Okay, so springs and dampers, these are the two main components that you'll have in any automotive suspension system. The idea is with the spring is to obviously provide a force to restore the vehicle to its regular equilibrium position. So you know with spring, if it's moved from its equilibrium position or its unstretched position, it's going to generate a force that pulls the spring back to its equilibrium position. So that's good, regardless of how the vehicle moves, it's going to want to go back to its equilibrium position. Now we also know from our ordinary differential equations courses that unless there's some sort of other mechanism, there's going to be an oscillation that actually perseveres for quite a duration of time. That's why there's dampers. This is to make sure that the oscillations are damped out so that once the spring returns back to its equilibrium position, it doesn't oscillate around the equilibrium position for an extended period of time. These dampers make sure once you have a bounce, a jounce, or a bump, that the equilibrium position the vehicle goes back to its equilibrium position as fast as possible. And these dampers are the tool that allows that to occur. Now, most dampers in an automotive utilize a piston rod cylinder arrangement where it uses some type of fluid, normally oil, to act as somewhat of a damper. Now, in some vehicles, particularly vehicles manufactured by General Motors, that's Chevrolet and Cadillac, the oil actually has some sort of ferrofluid material, or ferrofluid. It has a ferrofluid material in it. What does that mean? Well, it's oil that has metal particles or other magnetic particles in it. And actually, if you apply an electric current through such a damper, you can actually change the damping properties based on the amount of current you're running through the fluid. So this is what's used in I believe it's the Camaro, the Corvette, and what was the Cadillac CTS-V, I believe now the CT5V, use what's called meteorological dampers. Basically, you can control the damping rate based on the electric current being run through the ferrofluid. It's pretty cool technology, and actually one that GM is actually ahead in the world in terms of utilizing, which is surprising because GM doesn't really make good quality products anymore. I didn't say that. I still do drive a CTS-V myself. Anyways, springs and dampers, the main components of a suspension system. Now, what about some suspension terms? Pitch. We're going to talk about 3 terms, and these are all about different rotations the vehicle can experience. Since there is 3 axes, we live in a 3D world, 4D if you consider time, but in terms of coordinates or physical space, we live in a 3D world, so there's 3 different types of rotations a vehicle can experience. The first is pitch, and that is rotation of the vehicle with the nose or tail moving upward or downward. When we dive, that is the forward tilting of a vehicle during deceleration. So if you're going fast in your vehicle and you slam the brakes, your vehicle is going to dive forward, i.e. your nose is going to tilt downwards, and you're going to get a lighter rear end. A squat is a backwards tilting of the vehicle during acceleration. If you accelerate your vehicle rapidly and you have a vehicle that's powerful enough, you will feel your front end lift, or the weight will transfer to the rear wheels as you take off. If you have a very powerful car, such as that would be on a drag strip, you can actually lift the front end in the air. Now, that's not really to do with anything in terms of the aerodynamics of the vehicle or weight transfer. That's more to deal with the drive shaft riding up on the differential, but that's something else. So we have dive when you decelerate hard, or squat when you accelerate hard. Vehicles can't necessarily always squat if they don't have enough power. Yaw. Yaw is the rotation of the vehicle around the vertical axis, so perpendicular to the road. And roll is a rotation of the body from side to side due to lateral forces. We do this, look at this other diagram of this red vehicle over here. We see it's experiencing roll as it's trying to go through a corner. Now, if we had a perfect suspension system, the only rotation a vehicle would ever experience is yaw. Both pitch and roll are undesired rotations that are caused because of the other physics going on the vehicle. If we had a perfect suspension, perfect steering system as well, the only thing we would experience is yaw, i.e. we would just be able to pivot our vehicle around its central axis and turn. Now, this doesn't actually exist. There's always going to be some amount of roll and some amount of pitch, but essentially a performance-oriented suspension system will try to minimize pitch and roll as much as possible. So the only desirable rotation is yaw. Pitch and roll, not desirable. Okay, roll center. This is another important concept. So the instant center. So it's a point around which a wheel and tire assembly pivots during suspension travel. It's found by intersecting the pivot points of the suspension assembly. So down below we have 2 wheels, and let's say these wheels have 2 linkages connecting the suspension system to the frame. Well, if you draw a line that extends these suspension members, you will find the instant center. You see here, same thing, the green lines going from the 2 suspension members on the wheel on the left eventually goes towards the instant center, the point where all the green lines converge. And for the right side, we have these purple or pink, I suppose, lines that go until you get the instant center where they all converge. So that's the instant center. We have the roll center. a point located along a longitudinal axis around which a section of the vehicle rotates when cornering. Now this is found by intersecting the tire's center of contact with the road, i.e. the center of the contact patch, and the suspension instance centers. So let's look at the left side first. We have the center of the contact patch with the tire, and we have this green line that then extends to the instance center. We then have another pink line starting at the center of the contact patch of the tire with the wheel. That is drawn to the instance center for the right tire. Where those two lower lines, the lines that extend from the contact patch to the instance center, where those intersect, that is the roll center. Now you can see, since the vehicle is turning around, particularly for this particular diagram, the roll center is not actually in the center line of the vehicle. Now because of that, you're automatically going to have some amount of roll. Unless the roll center is perfectly in the center of the vehicle, the physics dictate that you must have some amount of vehicle roll. So one of the goals of the suspension design is to make that roll center, no matter what conditions the suspension find themselves in, as close to the actual center line of the vehicle as possible. Now that's an impossible job. There's no suspension in the world that you can design that under all conditions you will have the roll center near the center. However, you can try to optimize it as much as possible. Also note, as you try to keep the roll center as close to the center as possible, you're also sacrificing passenger comfort, because in order to achieve that, you generally have to have performance-oriented suspension, which is not as soft, as you would say, or as comfortable to ride in. So instance center, roll center. So now I'm going to talk about a few things that are related to the alignment, what's called alignment of the suspension, or in other words, how the suspension interacts with the tire and how the tire is aligned relative to the ground and the vehicle itself. So the first one I'm going to talk about is wheel camber. So camber is an angle of the wheel/tire with respect to the vertical plane. If you look straight forward at a wheel that is connected to a vehicle, the camber is the angle with respect to the vertical line. So camber angles are generally very small, approximately only 1 degree or so. Why do we have camber? Well, it provides directional stability, but if it's incorrect, it can also cause irregular tire wear. What I hate seeing on the road is when you see someone who's driving traditionally an import type car and you see their wheels look like they're about to tilt and fall off. They have an excessive amount of negative camber. I hate this because this is actually incredibly unsafe and has no performance benefit whatsoever. For some reason, this has become a fad of people where they want to have their wheels with excessive negative camber. This is not good from a stability standpoint or a performance standpoint, and it's just outright dangerous. But apparently that is what some people think looks good. I think it looks terrible, but you know, whatever. So positive, negative camber. Generally, we only want a very small amount, and just to provide some directional stability. Also, I should mention if you have a ton of negative camber, you're going to wear the inside of your tires extremely fast, and you're going to be running through tires much quicker than you should be. Whoops, sorry about that. Where are we going? Okay, steering axis inclination. Sorry about that. This is the angle from the vertical plane defined by the center line passing through the upper and lower ball joints. So how do? We have the upper and lower connections from the suspension to the vehicle. We have a line that goes through those upper and lower control points. And then we create another line that passes through the tire center line itself. So we want to measure that angle. So a reduced offset offers several advantages. It reduces the scrub radius of the tire with the road surface. A reduced scrub radius is a good thing. It reduces imbalance twitch as obstacles are encountered, and reduces road shock transmission to the steering wheel. Front suspension will also lift in proportional to the body as steering angle is changed, and this is another benefit. So we want reduced offsets when we look at steering axis inclination. Wheel caster. This is the angle between the vertical plane viewed from the side of the vehicle and the upper and lower joints. This impacts directional stability and also steering wheel returnability. Incorrect caster, though, can cause excessive steering effect. So when you go to turn the wheel, it's greater than you expect, and excessive tire wear. So if we look at this as the front of the car, if we look at the upper and lower control joints, depending on if it's positive or negative cam or wheel caster, sorry. Now, how you might want to set the wheel caster is somewhat defined by the drivetrain. If you have a rear-wheel drive vehicle, using positive caster means that the driving thrust from the vehicle helps to self-right the steering front wheels to a normal, straightforward driving position. So we have positive caster of rear-wheel drive vehicles. Negative caster of front-wheel drive, when cornering and removing the applied thrust, the opposing forces, i.e. the turning moment and rolling resistive forces, self-rights the wheel alignment, in theory. In practice, practical applications, most front-wheel drives still have a small amount of positive caster or none. So even though negative caster would seem to be in theory good for front-wheel drive, in practical applications, front-wheel drive just has a very small positive caster or none. Then finally, there is wheel toe. So wheel toe is defined as the difference in distance between the leading edge of the wheels and the distance between the trailing edge of the wheels as viewed from above the vehicle. So toe in means the front of the wheels are closer than rear. Rear-wheel drive vehicles tend to toe out. Thus, a small positive toe is used to counter this. So since rear-wheel drive vehicles want to toe out, we put a bit of toe in to counteract it. Toe out means the front wheels are further out than the rear. Front-wheel drive vehicles tend to toe in. Thus, this is compensated for with a small amount of toe out. Now, here's a video about wheel alignment summary. It's going to summarize the concepts I just discussed. Again, please pause this video and you can watch the video that is posted to Blackboard at this time. Okay, so I hope everyone watched that video on wheel alignment. It summarizes what I just spoke about, and it gives it more of a, I always find it easier to understand those concepts with a video rather than static slide images, so I hope everyone watched it. I'm now going to talk about traditional or common suspension systems that are used in automotive vehicles. So the first design, which is probably the oldest design, is called the leaf spring suspension. So this consists of a series of leaves or spring steel blades which are laminated together in various configurations. So during operation, each leaf is designed to slip or slide with respect to the next. With varying curvatures from leaf to leaf, you can get different spring rates. And this is generally applied to solid axle vehicles. What does solid axle vehicle mean? That means the axle connecting the wheels on side to side is one solid piece, is one solid pipe or axle, as you could call it. So in other words, this is cases where basically because the wheels are connected by a solid axis, the wheels cannot move up and down independently. In leaf spring applications, you generally have a solid axle, which means that if one side experiences a bump, the other side will as well. So, at this time, I would say you can look through some of the different implementations of leaf springs. However, these details are not something I want to focus on. Here's some more details about potential different leaf spring applications and some different ways of implementing them. Again, here's some more blowouts of some of the important components that are used in leaf springs. Again, I'm not too concerned with looking at the details of the components of the leaf spring system. Okay, so what we just talked about for leaf springs, it leads to what's called a dependent suspension. As I said, because it's a solid axle, if one wheel experiences a jounce or a bump, the other wheel has to move up because they're connected with a rigid axle. People in events, when vehicles were first being introduced, all of them were dependent suspensions, front and rear. Eventually, people realized once vehicles started traveling at higher rates of speed and greater cornering velocities, that this really was a problem for traction. You can imagine if you're trying to go around a corner at a decent speed and you hit a bump, well, one wheel flies up in the air and the other wheel flies up as well. You just lost traction. So people realized, well, this is not a very good solution, so we need to come up with an independent suspension system, i.e. where each wheel can move up and down, left to right, independently. And the first thing that was targeted was an independent front suspension, because generally the front wheels were responsible for steering, and that was very important for safety. So why do we move towards an independent front suspension? So this is the main one, is the driving conditions experienced by one wheel does not affect the other. Thus, it's easier to maintain traction. It can isolate each wheel to reduce unsprung mass. You can use a small package of springs due to increased stored elastic strain. And finally, the engine drive and drivetrain can be lowered to reduce center of gravity with using an independent front suspension. What are the disadvantages? You can't generate as much power during corner due to wheel cambering with roll. Tire scrub will occur due to wheel jounce, causing change in track width. You need a more rigid subframe / structure. It's a more complicated, which leads to higher cost. Unbalanced wheel assembly / vibrations will easily transfer to the steering wheel, and steering geometry / alignment is more critical. Now, you notice a lot of these disadvantages, just more rigid, more complicated, more critical. So it's not that these can't be overcome. These disadvantages can easily be overcome. You just have to spend more money, and it's more complicated. Now, most modern vehicles, regardless of whether it's a truck, whether it's a sedan, whether it's a van, are going to use independent front suspension. It's just safer because you have more traction. So most vehicles nowadays do not include leaf springs for the front suspension. They use independent front suspensions. So now that we've said independent front suspension is good, well, there's different implementations of how you can do this. One is, well, the first one is really kind of not exactly an independent front suspension. It's somewhat independent. It kind of is a bridge between leaf springs and true independent suspension. This is called a torsion bar. This is used a lot in more economy vehicles, or vehicles where cost saving is the most important and where performance is not really critical. Vehicles of this nature will use what's called a torsion bar system. Again, I'm not too worried about understanding the individual components of a torsion bar system, but I am more concerned with just an appreciation that this is one type of independent front suspension. Oops. The next most complicated is the McPherson strut. And now this is an actually fully independent suspension. It's simple, it's cheap, it's compact. Performance isn't as great as the other options I'm going to show you, but it's simple and cheap. So a lot of vehicles use McPherson strut as the front suspension, independent suspension, simply because it's cheap and simple and compact. Basically what it does is we only have one control arm which connects to the wheel spindle or stub axle, and we then have a compact structure which includes the damper and the spring, which is connected up top to a mounting normally underneath your engine bay. In other words, there's not a separate control arm. There's only really two pivot points in the entire suspension system. The one going from your frame and the one going to the stub axle. So the reason the McPherson strut is not great as performance because you only have two pivot points where you can possibly have motion. Now it is cheaper because you don't need extra components. You're simply bolting it up to the top, one of the top frame members or the top body structure underneath the hood. So it's cheaper. Then there's the double wishbone or short long arm suspension. So double wishbone suspension is based on the wheel hub and knuckle assembly being linked to the chassis through ball joints and control arms. Essentially, you have doubled your amount of connection points in the suspension system. Instead of just having connections on the lower half, you also have connections on the upper half or an upper control arm as well. The main benefit of having an unequal control arm length is a maintained track width, which is important for performance-oriented applications. So generally, double wishbone is more geared towards performance orientation rather than other applications. Here's more details on the individual components in a double wishbone. Again, I'm not as concerned with knowledge of the individual components. However, you are free to look at these if you wish. And then the most complicated is called the multi-link. This is where we have more than two links, so at least 3 lateral arms and one or more longitudinal arm that is connected to the vehicle. So this is the same tire assembly with the same suspension geometry, both from a side view and a top view. And it shows that in this case, we have 1, 2, 3, 4, 5 connection points between the wheel assembly and the body of the vehicle. This means you can control the motion of the wheel as it goes through a bumper or jounce much more finely. You have much more fine control over the travel of the wheel system. So now I'm going to go through the independent front suspension comparisons. I've already talked about a lot of these comparisons, so this shouldn't be too surprising. So torsion bar, again, we said simple, cheap, it's compact, but it's not truly independent. And this is mostly used in the rear of vehicles. So if we want to have a rear and somewhat independent rear somewhat independent suspension, we tend to use torsion bars. McPherson strut, again, simple and cheap. It's truly independent and it has a compact structure. Negative, well, it's not as good performance as the other options. Double wishbone, this causes increased negative camber while cornering. This is better traction, but it is more complex, means more cost. As you can imagine, for multi-link, we have more option for wheel alignments as wheels move up and down. This is better performance, but it's much, much more complex. Therefore, it's much more costly. So the type of vehicles that would implement a multi-link are vehicles that are aimed at the top levels of performance. Double wishbone, medium, and McPherson strut as well, simple, more simple performance. Torsion bar is definitely on the low end. Now, remember at the very beginning when we talked about the different ways a vehicle can rotate, we said roll was never desirable. But we said the problem was with almost all suspension is that when you go to corner, the roll center is almost never at the actual center line of the vehicle, and therefore you're going to get roll. So the way, or one of the ways to improve or reduce the amount of roll in a vehicle is to use what's called an anti-roll bar. So essentially it's an additional bar that links together other suspension components to reduce the amount of roll that a vehicle will experience during either cornering or a bump. Now, I'm not too concerned with everyone knowing the way in which a roll bar works, but I'm more just concerned with everybody understanding that roll bars are a consideration if you want to reduce the amount of roll that a vehicle experiences while going around a corner or going over a bump. Most performance-oriented cars, my CTSV, AMG E63, and M5 would definitely have a roll bar. Whoops, again, this thing wants to keep clicking forward on me. Boo. Okay, so that was independent front suspension. What about rear suspensions? Well, independent rear suspensions can basically be classified into two global categories. The semi-independent torsion bar based. We can have a transverse swing arm, a trailing arm, and a semi-trailing arm. Again, here's some more details on them. I'm not concerned with everyone knowing the details. Or they can be a true independent coil strut based. The one way to do it is strut and link arm mounted coil spring. So this is kind of like a McPherson where we only have two pivot points and that we have the spring and damper are kind of a single unit that are then connected directly to the body. Then there is the more advanced, which again, same as the front rear suspension, we have a true multi-link suspension where we have multiple links connecting the vehicle. Now I don't actually show a multi-link suspension here. These are actually two either strut or link arm mounted coil spring. In this case, both of these act pretty similar to a McPherson strut. Now, if you do, in this case, use a link arm mounted coil spring, we can actually have a pivot joint where the damper is connected to the frame. This allows for another degree of motion. So a link arm is superior to a strut mounted coil spring in terms of being able to control and adjust the wheel travel as the suspension goes up and down. So ticket out the door, something you learned today, something that was, or where the explanation was not clear or confusing. Thank you very much for paying attention to this lecture, and I'll see you next time where we will discuss steering systems. Thank you very much for your time. Goodbye.